here was a plot where we looked at E versus rho. Okay, we have repeatedly visited that. We introduced that into CES EduPack itself. So you have metals in the far top right, ceramics slightly above it, but in terms of the modulus, but slightly lower in terms of densities. Then you have composites and polymers in the middle in terms of density and properties. And then finally you have foams, which are very low in density but also very low in modulus. So now if you end up using the first material index, E divided by rho, which is a selection line for tie rods, right? You can begin to see in practice what happens. You have steels over here falling on the line. You have aluminum alloys and magnesium alloys very close to that same line, okay, as for the steels. And so basically that kind of explains that for tie rods, why steels, aluminum alloys and magnesium alloys all end up roughly being the same. So basically if you select anything above that line, so it's better this way, you end up getting a better option, maybe. Take the second material index, e to the power half divided by rho, and take a look at this line that was drawn parallel to this line over here, okay, as a reference line. So you have a slope of 2, and that gives the selection line for beams. And it so turns out that if you just drag this down a little bit closer this way, it will turn out that magnesium alloys are better than aluminum alloys, okay, which are a little bit below that. But both of these alloys are better than steels, and that's what we saw in practice in that table for the previous problem. If instead you go to the third material index, which is e to the power 1 by 3 divided by rho, which is a selection line for panels, you basically come down to this situation where foams are best served by this panel. And so again, magnesium alloys are far better than aluminum alloys or steels. So for beams and panels, materials of very low density are more important than for tie rods. That's the summary. So that's why foams are not used for tie rods, but are preferred for beams and more so for flat panels. Okay. So that's the gist of how certain material classes work better for certain geometries than for others for any given loading situation. We have repeatedly looked at beams and tie rods. Let's take a look at illustrating this for panel as to how the equations are delivered or derived. Right? So you have mass as A times L times rho. L is specified, the width is specified for the panel, and so T is a free variable, right? So that's the free variable over here. Right? You have rho as a density, you have S as a stiffness, I is the second moment of area, and E is the Young's modulus. So applying a load over there on this panel, and what can be varied? You want material choice varied, you can vary the thickness, right? So the constraint is stiffness, right? F over delta, which is C times E times I divided by L cubed, and I is WT cubed by 12. Since T is the free variable, it can be eliminated, and if you do so in this equation over here, you can basically express mass as again a product of the function requirement, the geometry requirements, in this case now this W and L, and then you get this new material index, right? And so the reciprocal of that material index, e power 1 by 3 divided by rho, right, gives you an example of how that material index was derived for the panel. So overall, if you wanted to minimize mass, if you used the same volume function, you would just use 1 by rho okay, the reciprocal of that, okay, to compare. If you wanted to minimize the mass for a given stiffness for these three different geometries, we have seen through derivations at each of these three material indices how they can be derived. Just for minimizing the mass, you maximize each of these material indices. The same approach can be used for minimizing cost as well. You know, the mass is rho times V. Price is referred to typically in cost per as dollars per kilogram. That's how you buy things, whether it's potatoes or whether it's steel. And so the total cost, capital C, is dollars per kg times kilograms per meter cubed. Okay. And so the total cost is dollars per meter cubed. And that can be plotted as the x-axis against either modulus, for instance. And so if you wanted to minimize cost per given stiffness, you basically have a material index that's very similar to minimizing mass, except you have this price little c over here that is in the denominator. Alternatively, that whole c times rho can be expressed on using CES adiabatic as the x-axis. Okay. And so to minimize cost, you maximize these material indices. Moving forward, what we are going to do is to be able to look at 4 different case studies presented by some students from the mechanical engineering department of the University of Louisville that show how these material indices that we have looked at so far in module 1 can be applied in the context of selecting materials.